All right, hello AP Statistics. This is section 11.1 chi-square goodness of fit test. You're going to need your note sheet, graphing calculator, paper, pencil. Once you got that, you'll be ready to go. All right, I hate to take you away from the M&Ms. I know they look amazing, but we're going to talk about Las Vegas, Nevada, Mandalay Bay Hotel and Casino on the Strip. They have special dice that you can buy that say Mandalay Bay on them that were once used at the casino. Okay. After some time, they retire the dice and they sell them in gift shops or the Walgreens down the road. And when that happens, people like myself who are fans can buy them. Okay. And then really just for fun. And so I have about 3 dozen Mandalay Bay Hotel and Casino dice that were once used on craps tables. And what I want to know is, okay, are these fair dice? Okay. Or have they been altered in such a way since they've been removed from the tables, such that one side appears more often than others. Okay, having known that, what it does is allow people to make wagers that support those more common or less common rolls and possibly win more money. Okay, so however, these are retired, which means they won't appear again on the table, but had they done so, okay, and had they been returned to the Mandalay Bay Hotel and Casino, and you knew which sides appeared more often, then maybe you could make some more money, okay? But given that, here's what I'm going to do. I'm going to take the 36 dice that I have and give one to each one of my students and have them roll it 24 times, okay? You can see that the Mandalay Bay Hotel Casino logo's on the front. It's also written on there. It has, a serial number on it too. And all we're going to do is roll it 24 times just to see if they're fair, okay? And I'll do it. My 30 students will do it. And we'll get 31 sets of outcomes. My specific one, I had 3 1s. I had 6 2s. I had 1 3, 2 4s, 8 5s, and 4 6s. And again, that does equal 24. And my students did the exact same thing. Once we had all of our totals for the respective 6 sides, okay, we put all the data on the board and we made giant sums of them. Okay, now for the entire class, okay, I gave you my little sum of 24 and how they were, the breakdowns went. The breakdown for the entire class, okay, for the number of 1s through 6s that we had 119 moments where we got a 1, 142 where they got a 2, 107 that were 3, 124 that were a 4, 113 that were 5s, and 139 times we got a 6. Okay, so here's what we're looking at. Are these, okay, close enough together to say, you know what, there's not a reason for us to believe that they're not fair, okay? Or are they far enough apart from each other, proportionally speaking, where we would say, you know what, there's maybe some evidence to suggest that these are not fair, they're not uniform, that the proportion of one outcome may be different from the others, okay? So let us note that there are a total of, for this class, 744 rolls, okay? And if you divide it by 24, that will give you the 31 students and myself total who participated, okay? So to test to see if these numbers are close enough together to say that there's not a reason for us to believe that they aren't fair, okay, versus really maybe not being fair, we're going to do something called a chi-square test, okay? And you can see this formula is written above. It says chi-squared equals, and you have this big summation sign, observed minus the expected squared divided by the expected. And we have a degrees of freedom, similar to what a T distribution had, where degrees of freedom is n minus 1. And n is not the number of repetitions that we roll the dice. It's actually the number of categories that we have within our work, okay? And since our dice outcomes can have one of 6 outcomes on it, we'll say that our degrees of freedom in this case is n minus 1, which is 6 minus 1, or 5. All right, now what are we going to do? Well, to test this, we're going to write a null and an alternative hypothesis. The null hypothesis is that the distribution of dice outcomes is uniform, okay? That these are basically about the same, okay? And it doesn't mean they'll be exactly the same proportionally, but maybe pretty close, okay? Realistically, they're asking, is the proportion of getting 1s equal to the proportion of getting 2s, 3s, Or are these all the same, the proportion of getting each one of these outcomes? Okay, and I guess I could tie this proportion of 6 being equal to the 1. Or is there any moments where maybe one of these are not equal? Okay, maybe it's a little bit bigger or a little bit lower than what the remaining ones are. And maybe there's more than one that is not equal to the rest of the group. Okay, and that's what your alternative is. The distribution of dice outcomes is not uniform. Okay, so in symbols, we can kind of write a null in this way. However, it's not really possible to write an alternative because all we're trying to show is that one of these, at least one, is a not equal to sign. Okay, and it's really not possible for me to represent all the possible ways that you could have something not equal. Okay, and at least one time. Okay, you could, okay, potentially do a 2 proportion z-test, which you learned last chapter, with each of the respective pairs. Okay, meaning you could do it with the probability of getting a 1 versus a 2. And then you could test the probability of 1 and a 3, see if there's any differences, 1 and 4, 1 and 5, 1 and 6. And then repeat the same with 2 and 3, 2 and 4, 2 and 5, and 2 and 6. And the possible pairs that you could make, okay, to do a 2 proportion z-test would be quite a bit, okay? And so what this test does, and what makes it kind of nice is that I can do a chi-square test and just to see if there is some discrepancy somewhere, okay? And once I may know where that is, then I can do a follow-up test with a 2 proportion z-test with that irregularity that seems to occur within what we'll see as our chi-square values, okay? Now, with this, we also have conditions, okay? And what are our conditions? Well, first is very similar, random, okay? Were our dice rolls random? For the most part, I think they were, okay? I don't think there was any bias in terms of how these were rolled. They were shaken well by students. They were dumped onto a table where they bounced a bunch of times, and those are the respective outcomes we got, okay? Now, there is replacement with your outcomes. So once you roll a dice, and for example, if you get a 6, okay, that 6 goes back into the pool of outcomes when you roll it again, okay? Though not all moments like this will have a replacement. So if you want to do a replacement, or you cannot do a replacement, I'm sorry, then you'll have to do a 10% roll. And that will just really depend on the type of story that you have with respect to your chi-squared problem. But if you were to do this here, it is 744, which is less than or equal to 1/10 the big N. And the big N is all dice rolls. Okay, and can we roll dice for a long time? Yeah, I bet we can roll at least 7,440 times. Okay, now, again, we do have replacement, which means I don't believe this is necessary. Okay, however, not all cases will you have replacement. Okay, and if you don't, then you'll have to do that test. Okay, the last thing is this, and this is a new one. It says expected values have to be at least 5. Okay, now, what does that mean? Well, over here, okay, when I look back at our table, we have observed values. This is what actually happened in our class. Okay, if the null is true, I'm going to highlight the null here with a little star. If that's true, and all these proportions should be the same, how many of each of these outcomes should I get for my expected counts for our class? Okay, well, most students in this class figured out pretty quickly. If there's 744 total rolls, and I have 6 outcomes that should occur the same amount of times, 744 divided by 6 is 124. Okay, and I'm filling those in under the expected count. Okay, I definitely want to have that written there. And in the end, I'm going to look at these and make sure they're all at least 5, which they are. I'll put my check mark there, and all our conditions are satisfied. Okay, which means what are we going to do next? Well, we're going to find our chi-squared value, which is our test statistic. Okay, we don't have z's, we don't have t's. In this case, we have a chi-squared. Okay, now how do you find a chi-squared? I'll look at this formula above, and maybe I'll choose a different color here to make this more visible. I'll use green. But what we'll do is we'll take our observed value, subtract the expected, square it, and then divide by the expected. Okay, so if I'm drawing this right here, it's 119 minus 124 squared divided by 124. Okay, that gives me 0.2016. Okay, and you have to repeat that 5 more times. Okay, now some people will say, well, that's kind of a lot. Can I do this a little more quickly? And the answer is yes. You can use your graphing calculator to create some lists. And if you like, you can put these all in L1, your observed, and then in L2, I know it's tough to see over Caesar's Palace, you'll write the 124s, okay? And then you can do a command for your chi-squared. So I'll do that in just a second. I'm gonna fill the rest of these in, 2.619. Sometimes students will say, do I have to show the work for this? And you don't really have to show the work. However, there's going to be moments where you're going to be expected to handwrite this out on your test. And sometimes they're in the form of answers on your multiple choice. And sometimes, they'll just want a little bit more work for a free response. Maybe it's one of my tests. Okay. But I am almost done. So I'm just going to finish this real quick. I like the one I'm currently working on. It's 124 minus 124. That gives me a 0 in my numerator, which means I had an observed value that was exactly the same as our expected. And so that gives me a value of 0 for a chi-squared. And then I've got 113 minus 124 squared over 124. That gives me 0.9758. And finally, the last one is 139. Okay, and that gives me 1.814. Oops, too fast. Okay, so here's sometimes what books will ask or questions they'll ask. They'll say, hey, which outcome was a little bit, or maybe most strongly represented in terms of our chi-squared, okay? And so before we add these up, I'm gonna look at these and figure out which one had the largest value. It looks like, to me, the 3, okay, was the outcome that was furthest away of what it should have been, okay? In this case, it was much lower than what it should have been, okay? The one that was most consistent with what it should be was the 4, of course, because you can see that the 124 matched with the 124 perfectly, and it gave us the smallest possible chi-squared value, which is 0, okay? So you will never have a chi-squared value smaller than 0, assuming that all your expecteds are positive numbers, which I've always seen them to be. Okay. All right. Last thing we're going to do is we're going to add these all up. Now, for some of you, you said, you know what? I'm going to put these observed in L1. So I'm going to highlight that right there. I'm going to put in L2. I'm going to highlight this, my expecteds. And in my L3, okay, you can do kind of a quick little formula for this. Let me put L2 here. That looks a little better. Which is L1, your observed, minus your expecteds, L2, squared divided by L2. Okay, so make sure your parentheses only stay in the numerator. Okay, and once you do that, you'll find that once you hit enter, you'll get these items. Okay. If you want to add them all up, you can do a 1var stats L3. I know you know that command because we are almost done with the school year and you've probably done it dozens and dozens of times. But yeah, 1var stats L3 will give you a chi-squared value. Okay, and this is the sum. Okay, so make sure you just look up the sum of all these numbers, 7.935. Okay, now what does this mean? Well, let me do this. I'm going to draw a picture of a chi-squared distribution for a degrees of freedom of, which we found earlier, 5. Okay. Now, here's the deal. Since your chi-squared values can only be positive, okay, that means your graph has to be skewed at least a little bit to the right. Okay, you're squaring everything in your numerator, which means you can't have negatives. Okay, you can't have a negative value in your numerator. So we will skew things to the right. And if you consider your chi-squared and the respective degrees of freedom, we said this was 5. What we can share is that if you look at the peak, okay, which is kind of like your mode, okay, that is represented horizontally through a value that is always 2 less than your degrees of freedom. Okay, so in this case, Your degrees of freedom is 5. So if you were to go across horizontally to 3, that's where your maximum representation of values should be. I'm sorry that went too fast. Okay, now from there, what do I do? Well, this is a chi-squared value of 3. You don't have to draw that chi-squared part, just know that that is 3. And the one that we found for our test statistic is 7.935, which is way to the right. Okay, and because I'm always looking for values at that spot or more extreme, I'm going to shade to the right. Okay, so I will shade to the right, and my goal is to find that respective area. Okay, now I didn't mean to like spoil the party ahead of time, but if I use my TI-84 right here, I have a chi-squared CDF command. Okay, it's under second distribution. Okay, and then you got to go to 8. So what does that mean? Well, we got chi-squared CDF. Lower bounds. Okay, now I'm going to put LB here because I still need a lower bound. The lower boundary of this area is actually our chi-squared value, 7.935. Now, how far does it travel to the right from my upper bounds? Well, it kind of goes on forever. Okay, and so because it goes on forever, I can't put forever. Let's just put a big chi-squared value like 1,000. Right, and then finally, I got degrees of freedom, which we found earlier is 5. Okay, and when you do this command, it'll end up giving you your 4th step. Okay, 3rd step was your chi-squared value. Your 4th step is your p-value. In this case, it'll turn out to be 0.1599 rounded. All right, now there is a table that you can use. Okay. And I don't traditionally use it because oftentimes I find that my chi-squared value is off the table. And so I like using the command right here for your graphing calculator a little bit better. However, I would read the book, okay, or look something up on it to get the chi-squared table available to you. And just to let you know how it's used, even though I think traditionally it's much easier to use your calculator to get your p-value, okay? Now, given that, our p-value is 0.1599, and we have to either decide we're going to reject or not reject the null, okay? And because our alpha is typically 0.05, our p-value is bigger than that, so we will not reject the null. Okay, so I'm going to write that. Do not reject the null. Okay, and again, because my p-value of 0.1599 is greater than your alpha cutoff of 0.05. Okay, which means there is no evidence to suggest that, and then you're going to write the HA. Okay, what is the HA? The distribution of dice outcomes is not uniform. Okay, again, I don't know where it may or may not be different, but in the end, okay, there's not an evidence to say that they're not uniform. Okay, so we're there is no evidence of discrepancy. Okay, so there's evidence to suggest that the distribution of dice outcomes is not, big not, uniform. Okay, so yeah, the dice. Now, I don't usually say this, okay, because we don't want to say that we accept the null, okay, but here's what we're going to say. There's no reason for us to think that these are not uniform, okay? So there we go. All right, so This was a nice situation because it gave us outcomes where we expected them to all be the same, okay? Where all the proportions were supposed to be about 1/6, okay? That won't always hold true with respective problems that deal with chi-squared, okay? So again, we had a chi-squared, we have degrees of freedom of 5. Keep in mind that you will have other chi-squared values where your degrees of freedom may be different, okay? Maybe a degrees of freedom that are 7 or so, I'll just make that up. And know that, what does that do? And I'm just going to draw a little example here, degrees of freedom that is 7. That would mean that 2 less than that, which is 5, is where their peak is. Okay, that's where their mode is. So you're going to get a picture that kind of peaks at a different spot and then tails off to the right. Okay, so the more, I'll just say, the larger that your degrees of freedom is, I'll say the more symmetric it's going to look. Okay, and so it just depends on the number of categories that you have within your work.